Hello, everyone. So I'm going to talk about the fast protection schemes. Mostly I'll be talking on the subject of loop-free alternates. Can I ask a quick question? How many of you have either studied loop-free alternates or have deployed it? Do you mind showing? Okay, so it's about 20%, something like that. Good. What I'll be talking about mostly is improving coverage of loop-free alternates, because as you'll see later, one of the issues with loop-free alternates is the fact that typically you don't get 100% coverage just if you're using normal vanilla loop-free alternates. I'll be talking about some schemes to change that, to improve that. One of those is remote LFAs, or RLFA for short. Also a way of extending it further using Igp advertisements in the form of direct forwarding labels. And what I'll focus on in particular actually is improving coverage of loop-free alternates with automatically created Rsvp bypasses. And as I'll explain, these are created dynamically where there are gaps in the LFA coverage, so you don't have to explicitly configure these tunnels, which makes it operationally good. And finally, if there's time at the end, I'll say a few words about maximally redundant trees, because we're starting to work on those, and we've got some prototype code coming soon if people are interested in testing that. So by way of background, as you know, Rsvp fast reroute has been available for many, many years, and actually it's got some very good advantages. It's very simple. You get full coverage as long as there are at least two ways to get to your destination. And normally it involves creating a full mesh of Rsvp LSPs between the edge routers, or the PE routers around the network. You create this full mesh, you turn on fast reroute on each of the LSPs. Having said that, over the last few years there's been a lot of interest in IP or LDP fast reroute schemes, and that interest comes mostly from people who perhaps don't feel the need to turn on Rsvp because they're not interested in doing traffic engineering, and so they say, well, why should I turn on a full mesh of Rsvp LSPs between all of my edge routers only to use Rsvp fast reroute? Are there alternative schemes? And so that's how this sort of whole industry sprung up, of looking at all these IP and LDP fast reroute schemes. Having said that, one sort of side note is that in many cases, actually, just making the full mesh of Rsvp LSPs isn't too bad, and it might be the best option. That's often the case. So that's something to bear in mind. So this is an introduction to the principles of plain, sort of vanilla loop-free alternates. And in this diagram, we're looking from the point of view of traffic coming from this router S, which is the source, traveling to this router D, which is the destination. And we can see the metrics on each of the links in the network. And, of course, the router does SPF calculations and determines the best path for traffic going to this destination. And given the metrics, the best path from the point of view of S is to send it to router N1, and from there it follows the green arrow to reach its destination. When loop-free alternates is turned on, what this router does is it says to itself, let's suppose I want to protect this link. Is there an alternate neighbor to which I can deflect traffic in such a way that the traffic will carry on towards the intended destination without looping back towards me? And such a neighbor is known as a loop-free alternate neighbor, because he does not loop the traffic back. And as you can see, given these metrics here, if this router were to deflect the traffic towards here, in fact, this would send it towards the intended destination. And so we've got a valid loop-free alternate neighbor here. So that's good. And so what this router's doing, in fact, is, as well as doing his normal SPF calculation, he's also doing SPFs on behalf of his next-door neighbors to see what they would do with traffic to a certain destination. Identifying this as a valid loop-free alternate neighbor, he installs an alternative path in his packet forwarding engine pointing towards this destination. As soon as that link breaks, the alternative path comes to the front and becomes the valid forwarding path. And because it's all happening at the packet forwarding engine level, it's very fast. It's a few tens of milliseconds, 10, 20, 30 milliseconds. And in fact, at the packet forwarding engine level, it looks exactly the same as traditional Rsvp fast reroute. The way the sort of infrastructure is done is exactly the same, and that's why you get this fast convergence for this LDP or IP traffic. So that's the principles behind the loop-free alternates. Now, having said that, the next question is coverage. And so what I will be doing is I'll show several slides during the course of this talk which show this topology, and the only difference between some of the slides is that the metrics may change. So here we've got a metric of 1 on each of these links, and depending on what I'm talking about, sometimes you'll see different metrics and different problems that arise as a consequence and different solutions. And always we'll be thinking about traffic traveling from this router S, the source router, to this router D, which is the destination, and always we'll be thinking about the breakage of this link shown here, this link between S and R1 and what happens. Now if you look at this slide, you can see one of the problems that happens with loop-free alternates. Often people have small rings in their networks. There might be sort of interconnected rings with perhaps 4 or 5 routers on each of the rings. And here you can see that S in fact does not have a valid loop-free alternate neighbor for traffic going to this destination D, because if he were to send the traffic towards R4, then from the point of view of R4, it has got 2 ECMP paths to the destination. It doesn't know yet that this link has broken because the Igp convergence takes a certain amount of time. And so in fact, half of the traffic would go this way around the ring, half this way. And so this half of the traffic would end up sort of looping backwards and forwards between here, which is not a desirable situation. We haven't succeeded in protecting the traffic. And this is a very common thing with the loop-free alternates. Given typical topologies and metrics, you don't always get the full coverage. And so the question is, what schemes are there available to actually improve the coverage? And so one such scheme, which is what I'll talk about first of all, is the remote loop-free alternate scheme, or RLFA for short. And what this is doing is it's playing a trick. It's saying, okay, my next door neighbors are not valid loop-free alternate neighbors, but I will identify a neighbor which is not directly connected, which is why it's called a remote neighbor. And if I can get the traffic to that remote neighbor, I know that once it gets to the remote neighbor, the metrics are in my favor, and the remote neighbor will send it towards the intended destination. So that's the essence of it. Now, in order to talk about the remote LFA, I need to first talk about a couple of definitions. And so, first of all, from the point of view of source S, who's attempting to protect this link, we talk about P-space. And P-space is the set of routers that S reaches without using the S to R1 link, given the metrics that are in use in the network. So if S were sending a packet to R4, he would just use this link, so that doesn't use the link that we're protecting. If S was sending a packet to R3, it would use this link as well, so that's in the P space. R2 in this definition isn't in the P space because S could send traffic either way around the ring to reach R2, so it's not in the P space. Having said that, we can slightly extend the definition of P space because S is doing the protection, and so he can force the packet for the first hop in whatever direction he wants. He knows that this link has broken, and so he can force the packet to go here, regardless of what the Igp metrics are saying. And so in that case, in fact, he can reach router R2 as well, without the metrics forcing the packet back towards him. And so in fact, with this extended definition, with this extended P space, we've got 3 of these routers who are members of it. And then the other definition is what's known as Q space. And Q space contains the routers that can normally reach router D without needing to use this link between S and R1, given the metrics that are in force. And so you can see that R1, of course, would send the packet straight across to D, so he doesn't use that link, so he's a member of Q space. R2, if he was asked to send a packet to D, he would send it along the direct link to D, so R2 is a member of Q space, and R3, if you asked R3 to send a packet to D, he would send it in this anti-clockwise direction around the ring, and so he's also a member of Q space. And so actually, if there is overlap between these two sets, the P extended space and the Q space, the nodes in that overlapping set are known as PQ nodes, and those are nodes that can be used as remote neighbors from the point of view of the remote loop-free alternates. Because if we can trick the packet into getting to, for example, R3, once it gets to R3, the metrics are in our favor, and the packet will roll downhill in terms of the metrics to the destination D. And so the question is, how do you trick the packet into getting to router R3? How do you actually get it to R3 in the first place to play this trick? And the answer is that you use the Ldp LSP that leads to R3. The Ldp LSP whose destination is R3. And so in fact, the packet that you're protecting is tunneled inside that Ldp LSP, and then at R3 it pops out of the Ldp LSP, and R3 forwards it towards the destination, because once it gets to R3 the metrics are in our favor. Now in the case of IP traffic being protected, can see a question? Yes, I'll come back to that in a second, yes. So there's two cases, IP packet being protected and LDP packet being protected, and the second case is, yes, what you said, yeah. So in this case, let's assume it's a plain IP packet that's being protected. In that case, we put that plain IP packet onto this LDP LSP whose destination is R3, and this knows the label for that, just normal LDP distribution. And so probably this is doing penultimate hop popping, so the packet arrives here as a plain IP packet. This does an IP lookup, and then the metrics are in our favor, so the packet travels like this. So we've played this trick to protect this traffic. Then coming back to your question, if it's an LDP packet that we're protecting, then indeed you do have a label stack, because what you need to know is, first of all, there's the LDP label required to reach R3, but then when it reaches R3, there needs to be another label, which is the label that R3 expects in order to send the packet towards D. And so in order for that to occur, in fact, S needs to know the LDP label that R3 is expecting in order to reach D. S isn't directly connected to R3, so he doesn't know that normally. And so for that reason, a targeted LDP session is set up between these two routers. And implementations are such that this would be set up automatically. So if S identifies R3 as a remote neighbor that he needs to use, then this LDP session would be set up dynamically in order to exchange that label value. And so in terms of label operations, suppose the LDP label that R4 advertises to S, corresponding to R3, has a value of X, then S pushes that label value on top of the packet. Inside, you have a different label value, which is label value Y, which is the label that R3 advertises on this targeted LDP session corresponding to destination D. And so the packet travels to R4. Assuming we've got penultimate hopping, R4 pops that label. Packet arrives at R3 with this inner label value of Y. That causes R3 to send it to R2. R2, probably pops the label, and it arrives at the destination D. And so, again, for the LDP case, we've succeeded in protecting the traffic. So that's the essence of the loop-free alternate behavior. Now, having said that, of course, you can always think of scenarios where even the remote loop-free alternate doesn't give you full coverage. And so in this case, if you look here, I've actually changed the metric. So here I've got this metric of 8 between R2 and D. And so the consequence of that, if you remember the definition of queue space, the queue space has shrunk right back. The queue space before used to come all the way around here. This time it's shrunk all the way back because of this high metric. And now the P space and the Q space don't have any overlap at all. And so there is no remote neighbor that S can use. And so we haven't got the full coverage, even using remote LFAs. Having said that, in real networks, certainly the remote LFA does improve the coverage compared to just using the normal vanilla LFA. And in fact, if you examine the remote LFA draft, it reports analysis of 11 different service provider topologies. And in 4 of those topologies, the remote LFA coverage was 100%. But in the other ones, it wasn't. In the worst case, it was 78%. And the average of the 11 networks was 96%. So whether you get full coverage or not depends on the topologies. That's one thing to bear in mind with the remote LFA. Now, there is something you could do to solve the problem that I showed previously, where we've got this high metric between here and here, and so the P space and the extended P space and the Q space didn't overlap. And this is using a scheme which is something new. It's involving Igp Label Advertisements, which is quite a sort of hot topic at the moment. And with that, what would happen is that R2 would announce a strict forwarding label in the Igp. And so in the Igp, he's saying, if I were to receive a packet with label 100, the action that I will do is to send that packet to router D, and this is regardless of Igp metrics, which is why it's a strict forwarding label. It's, it doesn't matter, you know, what the metrics are. It receives the packet with label 100, it always sends it directly to D. And as I say, it advertises this in the Igp, in fact, and there's a draft here which talks about that particular use case. And so in this particular topology and metrics that we've got, that has solved the problem for us, because now basically S knows that if he can get the packet to R2 using the LDP LSP, then if he puts this label value of 100 underneath, then he knows that R2 will send it to the destination. So we've solved the coverage problem in this particular case. So having said all this, one thing that certainly we've learnt and the industry has learnt over the past few years, working on LFAs and developing it and so on, is that it's difficult to attain full coverage without caveats. It does depend on topology, it does depend on metrics, and it seems that the closer you get to 100%, the more difficult it is to make further improvements. I think actually a good analogy is if you take a substance which is at room temperature and you want to cool it down to absolute zero, to 0 Kelvin, getting it halfway to 0 Kelvin, halfway down to 0 Kelvin is easy. You just put it into a bucket of liquid nitrogen, and that's really cheap, and that gets you halfway there without any trouble. And that's very similar to the simple loop-free alternates. You get perhaps 50, 60, 70% coverage, and it's easy to set up. But then you want to go a bit further, and then you need to have the remote LFAs, and then I showed you examples where even the remote LFAs don't give you full coverage, and then you can turn on this directed forwarding label that I talked about. Even then, you may not get full coverage in all cases. So you've got this thing where you're stacking all these different mechanisms on top of each other in an attempt to get to the full coverage. And really, the fundamental problem with all of this is that we're sort of fighting against the Igp metrics. So, given the topologies that I've shown and the Igp metrics, often what was happening was that we were trying to force the packet, the wrong way around the ring, if you like, and the Igp metrics were just blowing the packet back towards us, and we're playing all these, slightly complicated tricks to sort of overcome this force of the Igp metrics blowing the packet back towards us. So that's really, one of the sort of issues, if you like, with all of these schemes, in my mind. Now, wouldn't it be better if you could have a scheme where the packet is launched into a protection path where, regardless of the topology or the IGP metrics, that path always takes the packet towards its destination without looping? And in fact, of course, we have a way. It's called Rsvp. Rsvp is source rooted, and so it doesn't matter what the IGP metrics are. You can make the packet go wherever you want. And so what I'm going to talk about is a scheme where we actually improve the LFA coverage to 100% simply by using Rsvp LSP where there are gaps in the LFA coverage. So it's a very simple scheme, and it achieves a lot. So let's have a look at that in a little more detail. And so if we look at this diagram again, where we had this metric of 1 everywhere, all around this ring, as I noted before, R4 is not a valid LFA from the point of view of S, trying to protect this link between S and R1. And so S, identifying that, in fact, he hasn't got a valid loop-free alternate neighbor, automatically sets up this Rsvp LSP to protect the link. And so this Rsvp LSP goes to router R1, which is on the far side of the link. And in so doing, we've succeeded in protecting the traffic. And it doesn't matter what the IGP metrics are. We've achieved our coverage. Now, if you want, there's also an alternative mode of operation where the Rsvp LSP is always created. If you don't want to use loop-free alternates at all, you don't have to configure it. You can still use this dynamic Rsvp scheme. So this is already available in Junos. So it's been available since 12.3, which was the end of last year. Very nice scheme to use. And very simple to configure. It's just one line of config to turn it on. You just have in the LDP path of the configuration this extra line, dynamic Rsvp LSP, and from that, the router's doing all of the work. It, on its own, is identifying where the coverage gaps are and setting up the LSP where needed. And this it does adaptively, so if the topology changes and more Rsvp LSPs are needed, it will set them up. If the topology changes the other way, like more links get added and the dynamic LSPs are unnecessary, then it will take them away as well. So it's fully automated, which is good. So basically, the properties of this scheme, just to recap, are that if a valid LFA for a particular destination is present, that's used. If no valid LFA is present, an Rsvp bypass is automatically created. And if the user doesn't want to use LFA at all, then they can use the automatic bypass to cover all of the situations. And as I say, the advantages of the scheme are simplicity and full coverage. You know that as long as there's some other way to get to the point of local repair, well, to the merge point, then you're okay. You're going to be covered. In terms of the number of Rsvp LSPs needed, it's not many either, because at most, even if you had 0 LFA coverage, at most you'd need 1 Rsvp LSP per link per direction. So if you've got a couple of hundred links in your network, that's a few hundred Rsvp LSPs, which is not many at all. Now, an interesting property of this scheme, I've been talking so far about unicast traffic, unicast LDP traffic in this case. In fact, the scheme also applies to point-to-multipoint LDP traffic, and so that's what I'll talk about next, how we use the scheme for the point-to-multipoint LDP traffic as well. So by way of introduction regarding the point-to-multipoint LSPs, in Juniper we've been pioneers of the point-to-multipoint technology, and it's very interesting because it represents a grand unification of MPLS and multicast. And as many of you know, we've had Rsvp signaled point-to-multipoint LSPs for many years in Junos, and we've supported link protection for those for a long time as well. More recently, we introduced LDP signaled point-to-multipoint LSPs. Sometimes these are known as MLDP, and we've had those for a couple of years as well. And what we recently introduced was link protection for those LSPs. The reason for this is that LDP point-to-multipoint LSPs are quite popular for IPTV distribution. People, have a sort of head end, and they need to distribute the IPTV channels to different POPs around the network. And the LDP point-to-multipoint LSP is quite convenient for that. And people are interested in having fast protection, of course. If a link breaks in the network, they want to protect the traffic. And so the link protection achieves that in less than 50 milliseconds. So let's have a look how it works. And it's quite similar to the unicast case that I showed you before, in that there's different ways of using it. What I'll talk about first of all is case one, where the link protection of the LDP point-to-multipoint traffic is achieved using a dynamically created point-to-point Rsvp bypass LSP. Then I'll talk about case two, where the link protection is achieved using loop-free alternates, which is actually the unicast loop-free alternate. And finally, case three is where you use these in combination. So if the LFA exists, if there's a valid loop-free alternate neighbor, that's what's used. And if not, an Rsvp LSP is dynamically set up instead to provide the coverage. So I'll step through each of these cases. And in each of these cases, I'll have a diagram similar to this. And so what we're considering is this green point-to-multipoint LSP, which starts here. So this is the head end or the roots, which is R1. And then it travels through R2, and then to R3. And then at R3 it splits, and you've got these two destination nodes, or leaves, which are R4 and R5. And in fact, on these links in green, you can see the label value that's been assigned for each link. So this is the value used by LDP for this particular point-to-multipoint LSP. So you can see it starts off with label 20. This swaps it to a label value of 21. That label value of 21 tells R3 that it must make one copy and send it here with label value of 22. Another one here with a label value of 23. And so let's look at this first case where we're using Rsvp LSP to provide the link protection. And so in this case, what this router does is he sets up an Rsvp LSP which follows the best path to this node R3 that avoids this link here that we're protecting. So always I'll be focusing on the protection of this particular link. And in terms of the label operations, the way it works is, suppose that the Rsvp LSP, which is a point-to-point LSP, as you can see, on this link here, the label value assigned by R6 to R2 to use for this section of the LSP is a label value of 100. And so in fact what R2 does is, in his packet forwarding engine, he's got his main entry with this label value of 21 pointing down this link, and then he's got an alternative entry in case this link breaks, which is saying take this packet with label value of 21 and push this value of 100, which is the Rsvp label, on top. So we're building a label stack. So this on top, this underneath. The packet is sent here, and R6 is doing penultimate hop popping typically, and so that pops this label value of 100. He pushes the packet towards here, and so the packet arrives at R3 with the original label value that he was expecting, this label value of 21, which was underneath this label, and so he just does the normal thing and forwards it towards his destinations. And so we've succeeded in protecting this point-to-multipoint LDP traffic in very low times, because it's done at the packet forwarding engine level. It's a fast reroute style scheme. So that was case one. Now, case two is where, rather than using Rsvp LSP for the protection, we're using a loop-free alternate path. And so here I've marked what the metrics are for each of these links in this triangle in the middle. And so R2, given these metrics, knows that R6 is a valid loop-free alternate neighbor. And so suppose the LDP LSP that goes to R3 has this label value of 100. I've reused the same label value as in the Rsvp case. It's exactly the same label operations. If this link breaks, this is the point-to-multipoint LDP label. this label value of 100 is pushed on top. This packet is sent here. This pops the label, and it arrives here with the original label value of 21, which was underneath, and so that gets to the destination. And so here we're using a unicast LDP loop-free alternate to protect this point-to-multipoint LDP LSP. Now, I guess one thing to mention is that, of course, if we've got lots of LDP point-to-multipoint LSPs, then they would all be protected by this same loop-free alternate path. And also, if there's unicast LDP traffic, it's also getting protected by this loop-free alternate path as well. For the Rsvp case before, again, if you've got lots of LDP point-to-multipoint LSPs crossing this link, then they are all protected by that same Rsvp bypass LSP. And then finally, case 3 is where you're using these two schemes in combination. And so if the loop-free alternate is available, it's used. In this case, given these metrics here, the loop-free alternate path is valid, and so that's used. If I change the metrics, let's have a different scenario. This is now a metric of 50, and so this is acting against us in terms of loop-free alternates. And so now this is not a valid loop-free alternate neighbor, because we know that this would just send the traffic back, which is no good. And so this router here, R2, automatically sets up this Rsvp LSP instead to act as the bypass. And this is happening, completely dynamically. It doesn't need any operator intervention. And so using this adaptive scheme, we've succeeded in bringing the coverage to 100%. So this is, a very good scheme for protecting LDP point-to-multipoint traffic. So just do a quick check on the time. I think I've got time to talk about a final topic, actually, which is an alternative way of achieving fast convergence to the LFAs, which I've been talking about, which is maximally redundant trees, or MRT for short. Can I ask quickly, has anyone sort of studied MRTs or read the drafts and things? Anyone heard of it? I think mainly not, so I'll give an introduction to it. So if you consider this network, and let's suppose the Igp metrics are 1, unless marked differently. So on these particular links, it's actually 10 instead of 1. And we're considering traffic traveling from this router S, which is the source, to this router D, which is the destination. As part of the normal Igp SPF calculation, what in effect is calculated is the shortest path tree routed at this destination, and that's shown with these green arrows. And so, for example, if S was asked to send a packet to D, it would send it to here, and this would send it here, this would send it here. So in effect, the shortest path tree from S to D is like this. With the maximally redundant trees, what each router does is also compute what's known as the blue tree and the red tree routed at this particular destination. And the red tree and the blue tree have the properties that they are as disjoint as possible, which makes them very good for acting as a fast reroute scheme. Because what happens is that if S wants to protect this link in terms of traffic going towards destination D, it knows that this blue tree doesn't use this link, and it knows that this actually takes the traffic to the destination without using the facility that it's protecting against. And so in this way, by either putting the traffic onto the red or the blue tree as a repair action, you take the traffic to the destination, and so it's acting as a repair mechanism. Now, in fact, what actually signifies these trees in the forwarding plane, it's labels, for example, LDP label. And so what would happen is that each router, rather than announcing just one label associated with its loopback address corresponding to the shortest path tree, it would announce 3 different labels, one corresponding to the green tree, one corresponding to the red, and one corresponding to the blue. Now, some interesting facts about the MRT. In fact, it provides 100% coverage for link and node failure, regardless of the topology and the Igp metrics, assuming there's another way to get to the destination, which normally there is. And so once the packet is launched onto the blue or red tree, it travels to the destination. Now, of course, each router in the network has to have a consistent notion of what is the red tree and what is the blue tree. They have to be consistent for the packet to actually successfully reach the destination along one tree or the other. And so an algorithm's been defined such that the nodes have a consistent notion, and that's described in this particular draft. Now, in terms of computing the trees, it's a sort of add-on to the normal SPF calculation. So when the router's doing the SPF calculation, it calculates these trees as well, with some extra processing steps. One interesting property, actually, is that it's relatively easy compared to, say, LFAs to answer the question, what path will this traffic take to get to this destination if this particular link or node breaks, especially with tree tracing tools that we're planning to provide. So you sort of know in advance what the path would be if, let's say, a particular link breaks. Now, if you wanted, in principle, you could use this as a supplement to loop-free alternates. If you've got loop-free alternates turned on, you could use this as a supplement to deal with cases where you haven't got full coverage with the LFAs, or you could use it as a complete alternative. So those are two modes of operation. Now, another interesting thing is how do you actually distribute these label values? So how does a node advertise the label for the red tree and for the blue tree, and how does it distinguish between them? And there are two possible methods. I guess the method that was first of all proposed is using multi-topology LDP, where in fact you're choosing different next hops based on both a multi-topology ID and the FEC. And so in effect you're saying this is the label associated with the red topology, and it's got topology ID associated with it. This is the topology, this is the label for the blue tree, and also you're advertising the normal SPF label as well. A more recent proposal, which has just come out in recent months, is again using this new sort of technology, Igp Label Advertisements, and with that you're actually advertising the labels in the Igp, which is ISIS or OSPF. There's definitions for each of those. And if you look at the drafts that talk about how to do this for ISIS or OSPF, the label advertisement drafts make a provision for an algorithm ID field which accompanies the advertisement, and that can be used to identify the labels belonging to either the red MRT or the blue MRT. So that's an alternative way of doing it. So that brings me more or less to the end. I think I've used up more or less the whole time slot. So the main thing that I've talked about today, in fact, is loop-free alternates and the difficulties of extending the coverage of loop-free alternates to 100%. And I talked about the scheme where you can, in fact, use dynamically created Rsvp LSPs to improve the coverage. And that's now available in Junos. And furthermore, not only does it work for unicast LDP traffic, it also works for LDP point-to-multipoint traffic, which is a good bonus. Maximally redundant trees, this is technology that's been sort of studied in terms of IETF drafts and modeling and looking at algorithms for, I guess, a few years now, but now we've decided to take the plunge and have some prototype code, at least in the first instance. And so if people are interested in testing the maximally redundant trees, please get in touch. We can give you some prototype code. Also, we're going to put it on Junosphere, which is a sort of virtual system where you can build a network simulating Junos routers without having to actually have Junos routers in the lab, and we'll have MRT prototype code on that. And in some of the conferences, we're going to have live demos of the MRT over the next few months as well, which is something that could be of interest. Okay, thanks for your attention. I guess maybe we've got time for a question, if anyone's got a quick question. Otherwise, we'll move to the next speaker. Yes, there's a question at the back.
Matthew Moylecroft. Are there any scaling issues? Like, does this work? Does this have any sort of issues with very large, very meshed networks with lots and lots of paths? I mean, if it's very easy to turn on. If I've got 32-way paths or everywhere, or 64-way paths, am I going to start running into CPU issues on the REs and so on?
No, it should be okay. I mean, with the Rsvp LSPs, then basically, for each link you're protecting, in the network, in the topology. I mean, if you had no LFA coverage whatsoever, then the worst case would be that you'd need an LSP, per link, per direction, because the LSPs are unidirectional. So someone's got a few hundred LSPs, a few hundred links, that's a few hundred LSPs. I mean, even if they've got, ECMP paths and things like that, that should be fine as well. I mean, vendors, publish, scaling figures for how many Rsvp LSPs they can support, and they tend to be in the range of tens of thousands crossing a particular node. So that's easily comfortable for these schemes that I've been discussing. Okay. Another question?
Do you have any kind of tools which could help us to determine the coverage of the network in advance, before trying it in a real?
Right,
yes.
Right. That's a good question. So regarding assessing the coverage, once you have it deployed actually on the routes, as as a side note, you can see the coverage because basically, let's suppose we're just using normal LFAs, for example. Basically, for each destination, you can see what the coverage is, whether you're covered or not. And furthermore, it gives you a sort of summary. So basically, it will say, okay, you're covered for 89% of the destinations in this network or something like that. So you can see it like that. Now, in terms of sort of offline assessment, people either use these sorts of third-party vendor sort of modeling tools. What we've done internally is we've got a sort of tool that we've sort of built, which we've been using, just to help with the development work. So we may sort of, be able to share, that potentially. So that's an option. But there are these, tools that people can use to assess offline in advance. Yeah. Okay, I think we've probably run out of time. Has anyone got a final question? Otherwise, we'll stop the session and we'll have the next speaker. Okay, I think that's it. Okay, thanks a lot for your attention.